This segment focuses on applying the knowledge that we've learned in the last several segments about enantiomers, diastereomers, and constitutional isomers towards solving problems related to identifying the relationship between two different molecules. For this segment, we're going to be looking at the worksheet or handout that indicates that we should place an X in the box that best identifies the relationship between the two molecules from each pair below. We're going to walk through each of these problems, and it would be a good idea for you to go through and try to do this yourself to start with, and then come back and review the answers to see how close you got to the mark for this. So let's go ahead and get started on looking at our first problem here up top. Place an X in the box that best identifies the relationship. And the possible relationships we have are that the two molecules are identical or conformers. Remember that conformers mean that we can totally superimpose all of the atoms. In other words, the two molecules become identical by just rotating around carbon-carbon bonds. So conformers mean that we can just rotate around carbon-carbon bonds to make the molecules identical. So we'll closely investigate each pair of molecules to see if there's some way we can rotate around the carbon-carbon bonds to make the two molecules the same. Diastereomers are going to refer to molecules that are related to one another as the cis and trans flavors of the molecule. Or they're going to refer to situations where we've changed some, but not all, of the RS chiral centers. Enantiomers are going to imply that we're creating non-superimposable mirror images. To create non-superimposable mirror images, that means that we're changing all the R's to S's or S's to R's. In other words, all the wedges are becoming dashes, or all the dashes are becoming wedges. Or the other way to look at it is we've created mirror image that are non-superimposable on the starting structure. Constitutional isomer means that we have changed the connectivity between atoms. So delta for change, connections between atoms. So we've changed the location of where the branches are, we've changed the size of the ring, or we've done something to totally move around atoms within the molecule. So we've changed the connections between atoms. We've gone beyond just changing how they're oriented in three-dimensional space to actually moving the atoms from one place to another within the molecule. And then resonance structures, this is a throwback to a much earlier segment. Resonance structures imply that we have moved only electrons in going from one structure to another. So resonance structures are related by moving electrons from one place to another to yield different possible Lewis structures of a molecule. So we're going to try to establish what term here best describes the relationship between each of the pairs of molecules that we've shown. So let's get started with the upper left here. So in the upper left molecule, what you will notice is that we have definitely moved some atoms around in this molecule. They both have the same molecular formula, which is a prerequisite for all of these relationships that we're talking about here. So in this case, both of the molecules have the molecular formula C4, and both have one oxygen, and then counting up the number of hydrogens here, H8. So they're both C4, H8O, so they have to be an isomer of some sort because they have the same molecular formula, but a different structure of some sort. And the way the structure has changed here is that we've taken a hydrogen right here, and that hydrogen is no longer in the structure over here. Instead, it has moved over to here because what was originally a CH group has become a CH2 group. So therefore, since we've moved atoms from one place to another in the molecule, we refer to the relationship here as being constitutional isomers. Let's come down to the next problem. So in the next problem, we ask ourselves what the relationship is between these two molecules. And we see here that we have two structures that have the same connectivity between atoms. In other words, if we were to count off the atoms here, we have carboxylic acid coming off at carbon 2 of the chain that we're identifying here. This isn't necessarily how to number this for IUPAC nomenclature or anything. I'm just numbering the chain consistently between the two. So we notice that in both of them, we have a carboxylic acid branch coming off and an amino branch at carbons 2 and carbon 3 respectively. So these two are definitely not constitutional isomers because of the same connections between atoms. We see differences in how the wedges and dashes are arranged here. So we have to ask, do those differences in wedges and dashes allow these to constitute identical molecules, diastereomers, and enantiomers, or what's going on here? So in order to address this, we can ask, are these mirror images of one another? They are definitely not mirror images of one another, because to be mirror images, the way that we've drawn these would require that for this to be the left and right-handed versions of the molecule, this would have to be a wedge, and this would have to be a wedge to make it a mirror image of the structure on the right. So they're definitely not enantiomers, so we can rule that out. Are they diastereomers? Have we changed the stereochemistry at some of the chiral carbons, but not all of them? The answer I can give you to that is no, we have not done that. So these two molecules are going to turn out to be identical molecules or conformers. And one way to approach this is by just visualizing it. You can envision, you could flip over the structure on the right to make it totally superimposable to the structure on the left. These two are totally equal if you flip over the one on the right. The other way to address it is to systematically go through and assign all the chiral centers as R or S, and if they're totally the same, then the two molecules have to be totally the same. So we could go through and we can assign this chiral carbon as being an R or S chiral carbon. And if you were to go through and assign this chiral carbon as being R or S, what you should see is that this is an R chiral carbon. If you come in and do the same thing right here, what you should see is that that turns out to also be an R chiral carbon. And then if you come over here and do the same thing, you're going to find that this chiral carbon is assigned as R. And you're going to find that this chiral carbon is also assigned as R. So the stereochemistry is identical between the structure on the left and the structure on the right. Therefore, they are identical molecules or conformers of one another. It's just two different ways of drawing the exact same molecule here. So that's one reason why assignment of R and S can be really useful, is it can help you pick out the relationships between these different molecules. If you're not good at just mentally flipping over the structure, or you don't want to build a molecular model of it to identify that, you can do this assignment of R and S to sort that out. So these two molecules definitely identical or conformers of each other. Coming on down to the next structure. So we look at these two structures and relate them to one another, and we look at the structure on the left, and based on what we learned previously about the stereochemistry of cyclomolecules, we could describe this molecule as being cis because of the fact that there's a wedge here and a wedge here, meaning that both of those groups point toward us. They're both on the same face of the molecule. On the other hand, over here we have an OH group and an H2 group, both as dashes. I'm sorry, one as a dash, one as a wedge. Therefore, we describe this molecule as being trans. And if we have two molecules and we can describe one as being cis and one as being trans, automatically look no further than saying that they have to be diastereomers. That is assuming that the branches come off of the same places, and they do. We have a branch at carbon number 1 with the alcohol group. 2, 3 is where our amino group is. Alcohol group carbon 1 in the ring. 2, 3 is where our amino group comes off. So they are branched at the same places, so therefore they have to be stereoisomers of some sort, and diastereomers what we come up with because they are related as the cis and trans versions of the molecule. All right, coming on down to the next one here. You're going to be really tempted for the next two problems to identify these as conformers, because in an earlier chapter we used Newman projections as a way of showing different conformers of a molecule. But Newman projections don't always have to show conformers. They could show other types of relationships as well, such as they could show two different constitutional isomers. They could also show enantiomers or diastereomers. So we need to sort out what's going on here to relate these two structures from our two Newman projections. So first off, we asked, do they have the same number and type of atoms in both molecules? In other words, do they fit into any of these buckets, any of the categories up top? They do, because they both have the same number and type of atoms. They have to be an isomer of some sort. And as we look at the two structures, we look at the carbon atoms bonded to the carbon in back, and I'm going to highlight those in red. So remember that the circle indicates the carbon in back, and whatever connects to that circle is what's bonded in back. So what's bonded in back is everything that I've shown in red. We can do that over here. So draw your circle, and then what's connected ending at the circle is what's bonded to that carbon atom in the back of our frame of reference. So you have these two. Those two groups look identical. They're even oriented the same. So now let's look at what's bonded in front. And remember that what's bonded in front is what comes to the middle of that Y. So what's bonded in front is going to be our ethyl group that's directly bonded to the carbon at that center frame of reference, CH3 and H. Here we have CH2, CH3, our ethyl group, methyl group, and our hydrogen atom. So how are these two groups related to one another? In order to establish that, what we can do is rotate around the carbon-carbon bond that is our frame of reference there, the center of our Newman projection, and we can determine whether by rotating around the carbon-carbon bond we can totally superimpose all the atoms. If we can, then the two molecules are conformers. On the other hand, if the best we can do is make a mirror image, then the two molecules are enantiomers. So let's take one of these two structures and rotate around the blue airplane propeller on the front. Airplane propeller meaning that Y shape, we can rotate around that. So we'll go ahead and rotate that carbon-carbon bond that is our frame of reference. When we do that, we're going to leave the atoms in back right where they were to start with. So I'm just anchoring the atoms that were in red. And then the atoms in front, we've rotated around, and we can rotate around by, say, moving the ethyl group up to here, hydrogen down to here, methyl group over. So we're just rotating around the carbon-carbon bond to do that. I'll show, based on the green arrows that we've shown for rotation, what we come up with by doing that. By doing that, our methyl group would come over to here. Our CH2, CH3 group comes up top, and our hydrogen comes to right here. Now if we look at this structure that we've just drawn, or redrawn for the molecule on the right, once we've redrawn that by rotating around the carbon-carbon bond, we'll see that it is indeed totally identical to the structure on the left. So if you can do some rotation around that carbon-carbon bond that's our frame of reference and make the two molecules totally superimposable, then that implies that they are indeed conformers. So we're going to mark off conformer as the relationship between these two structures, because that structure that we redrew on the right by just rotating around carbon-carbon bonds totally matches the structure in the green box on the left. Let's go ahead and do a similar exercise for this pair of molecules down below. So in this case, we take a look at our atoms here, and I'm going to go ahead and color code the same as I did before. So the atoms in back are in red. Everything that's bonded to that last carbon, the carbon behind us in the frame of reference, that giant circle, bonded in red. Show the same thing over here. And you'll notice that in the back, we've totally aligned all of our atoms. So that's good to go. Then we go ahead and do the same exercise with the atoms bonded to our front carbon of the frame of reference. So I go ahead and fill in all of that info. So I'm just highlighting everything in blue there. I'm going to do the same thing over here just to keep track of who's who and who's where. Okay. Now, at this point, we ask ourselves, if we rotate around the carbon-carbon bond that is our frame of reference for one of these two structures, I'm just going to take the one on the right for convenience. If we rotate around that carbon-carbon bond, is there any way that we can redraw that so we totally superimpose all the atoms? Or, when we rotate around, do we find a way that we can create a mirror image of our starting structure? So to create a mirror image of our starting structure, what we're really looking at is we're creating a mirror image at the chiral carbon. And we have in this molecule one chiral carbon. That is the carbon atom that is in front here. So I'm putting a little star there in front to indicate our chiral carbon. So that's what we want to be able to see, that we can make a mirror image if the two are going to be related to one another as enantiomers of each other. So rotating around the carbon-carbon bond should indicate to us that either we create an enantiomer, or by rotating around the carbon-carbon bond, we create something that's totally superimposable with what we started with. So in this case, to try to line up everything, I'm going to rotate around my carbon-carbon bond by going in this direction. So I move everything counterclockwise by 120 degrees. I'm going to redraw my groups now that I've rotated that propeller of the plane by 120 degrees. That makes our CH2, CH3 group come up to the 12 o'clock position. That makes our CH3 group come over to here, and that makes our hydrogen come over to here. We rotated each of those 3 groups following the green arrows, taking them each 1 slot, going in the counterclockwise direction. Now we take a look at how this molecule that we've drawn relates to the structure that we've started with. And what we will see is that those 2 structures are mirror images of each other. Because if we look at how the atoms orient relative to one another, we see that this methyl group is down to the right, this one's down to the left, alpha group is up here, hydrogen atom down to the left, hydrogen atom down to the right. So these are mirror images of one another. And we could show that that back carbon, we could also go ahead and rotate that around to make a mirror image. We don't really have to though, because that's not a chiral carbon in back. The one that we have to focus on is the chiral carbon. That's what we have to be able to make into the mirror image. At the other locations in the molecule, it doesn't matter because those aren't chiral locations. So our chiral location needs to be a mirror image. And indeed, we can just rotate around to make those into mirror images. And therefore, if by rotating around what we make is a mirror image, then the 2 structures have to be related as enantiomers. So that's going to result in me filling in this box right here to wrap this up, that these are enantiomers of each other. So with this, hopefully what you've gathered is the ability to establish the relationships between any pair of molecules by applying the definitions that you know for each of these different terms. And in the worksheet, there is more experience and exposure to doing exactly this, and you are certainly expected to be proficient at taking any 2 molecules and identifying what the relationship is between those 2.